people. But before I did this, I realized that the problem was much, much worse. You see, I could find absolutely zero evidence that this very spot was ever the site of a mining claim or mine, an illegal dump, or an illegal mine. In fact, I could find zero evidence that this very spot had ever seen a human set foot here with mining equipment, meaning that this is not acid mine drainage but instead something else. As, by looking around nearby, I can find 5 other drainages, streams, and riverbeds where this same process is also occurring. And it is not exclusive to this mountain range either. The same process is also seemingly occurring at streams in Canada's Northwest Territories and at more than 5 dozen streams in Alaska's Brooks Range. And, while I could not detect this same process to be occurring in any of the countries listed here, the conditions are ripe for this same process occurring further down the line. Toxic metals. These rivers which have turned orange have become acidic, some highly acidic with a pH as low as 2.6. Additionally, many of these streams now have elevated levels of lead, arsenic, cadmium, cobalt, copper, and zinc along with downright toxic levels of nickel, aluminum, manganese, and iron. It should not come as a surprise that wherever these orange rivers appear, fish species decline or disappear. So, why are some of the planet's most pristine waterways suddenly becoming toxic and unsafe to drink? The answer relates to the thawing of permafrost due to ongoing climate permafrost change which has raised world temperatures. For reference, permafrost is a layer of ground that remained completely at a temperature lower than that of the freezing point of water for 2 or more years straight. Some patches of permafrost are as much as 700,000 years old, while the vast majority of the world's current permafrost is many tens of thousands of years old. Permafrost currently underlies 18 million square kilometers or 12% of Earth's landmass. Permafrost is an impermeable layer, meaning that groundwater cannot penetrate it while it exists. However, as worldwide temperatures rise, which is occurring nearly 4 times faster in the Arctic than the rest of the planet, this permafrost layer has shrunk. This has allowed 2 things to occur. First, bacteria. Large quantities of iron which were previously bound in a layer of permafrost become exposed to groundwater, allowing for it to become clustered together in higher concentrations where the groundwater flows. This allowed for large quantities of iron-reducing and cold-resistant bacteria to feed off of remains of previously frozen plant and animal remains, reducing the abundant iron-3 ions to iron-2 ions. The iron-2 ions then combine with oxygen to create a range of oxidized rust-colored compounds, which groundwater seeps then bring to the surface and into rivers, turning them orange and brown. However, pyrite and sulfides. Many of these permafrost regions also contain abundant mineral reserves, with one reasonably common deposit consisting of numerous sulfide minerals, one of which is pyrite. If pyrite is exposed to rainwater, it will react and turn the rainwater acidic. Since patches of pyrite and sulfide minerals previously trapped in permafrost are finding themselves now in the active layer, they are also being exposed to water for the first time in tens of thousands, sometimes hundreds of thousands of years. As a result, natural acid mine drainage occurs, and since pyrite often contains elevated levels of nickel, it carries large amounts of it and iron into regional streams. However, due to the increased acidity of the water by the pyrite runoff, other minerals that contain potentially harmful compounds become easier to erode by the water, adding other elements to the water. And this is why many streams in remote Alaska and Canada are turning orange.